Spotlight, lectures and performances on and around Albany State University.
All right, good afternoon, everybody. We're happy to have Mr. Chip Westberry from Farley Nuclear Plant join us today, and he's going to be discussing nuclear safety and energy. So, in terms of what happened a few months ago, actually last year, with the nuclear crisis in Japan, what sort of precautions do we have here in, say, Alabama at Farley Nuclear Site, which would prevent something like that from happening? Okay, Mr. Westberry, he's an engineering systems manager, and he's been over at Farley Nuclear Plant for over 28 years now. And he received his bachelor's degree from Auburn University in 1983. So if you would please join me in welcoming Mr. Westberry. Thank you.
Good afternoon to y'all. I'm here to basically tell y'all a little bit about nuclear power. We'll talk about the three different accidents that have happened in the industry over the years, so y'all understand that a little bit. There's handouts that I provided in the back, I think near both doors, that've got information for y'all, and then there's plenty of extra copies for, for the staff to have. All right, so let's talk a little bit about radiation first, just so you got an understanding of that. How many of y'all have a dental x-ray every year? Okay. You got more radiation than that dental x-ray than I've received at that plant in the 28 years I've worked there. And I've worked pretty close to the fuel at several times. I was in operations for a while, and I was in charge of actually unloading the fuel from the reactor core. So that means I was on a crane in about 40 feet of water above the fuel as we pulled it up into the crane and moved it and offloaded it into storage. So just understand that there's a lot of sources of radiation out there that you're normally exposed to. How many of y'all recognize, the bricks that you have in this building? They've got natural isotopes in those that give off radiation. If you live in the mountains, there's natural radiation in those areas also. So people that live up in the Rockies are going to receive a lot more natural radiation than the people that live on the plains like we do. But there's a lot of things that expose you to radiation on a normal basis. So, even though nuclear power does have a lot of radiation that they deal with, it does not get out into the environment on a normal basis to get to anybody. So there's nothing to be afraid of there. All right, so the industry has had 3 accidents since nuclear power started. First one was ThreeMile Island up in Pennsylvania. It happened in 1979. That's when I was in college, so I remember hearing about it a lot. What happened there is the operating crew in the reactor had some indications that they believed of what was going on in the reactor, and they had a valve that stuck open that relieved water from the reactor system, which basically dropped the pressure. Now this plant's what they call a pressurized water reactor. So what it does is it has water that's at a very high pressure, 2,200 pounds, and about 600 degrees, that they use to remove the heat from the fuel. Okay. Well, when this relief valve opened, it started dropping that pressure, and it allowed that water to turn into steam, and so it could not remove the heat from the fuel anymore. And the ultimate result of that accident is that core melted. Okay. There's a movie called China Syndrome that came out pretty close after that event happened that talks about a lot of different things, but a lot of this in that movie is not real. It's all made up just to be dramatical for the movie itself. But there are little things in there that are true. They do have enunciators, and then that happened a lot at this accident. And the people, we found out based on all the research they did following that accident, is the people did not have enough knowledge to properly operate that plant to the depth that they needed to. So a group called INPO, Institute of Nuclear Power Operations, was formed. It's based in Atlanta. So if you go up there to the north side of Atlanta, inside the bypass, you'll see that building. And basically they set up ways the industry was going to self-regulate itself. So all the companies that have nuclear power plants pay into INPO to have them do this for us. And that helps the NRC regulate the industry. What they found is that the industry needed a lot more training on different things and different types of accidents that could happen at plants. So now all the plants have simulators. The operating crews have to go through training usually every 5 or 6 weeks, and it's continuous. They never stop except for an outage. And they practice every type of accident that has been postulated to happen at a nuclear power plant. And if anything comes up new that's something that wasn't expected, they'll add that and they'll start practicing that too. So a lot of what's practiced are things that are never expected to really happen at a power plant. All right, so that happened out of 3-Mile Island. All right, the next main accident that happened was Chernobyl. I'm sure y'all have heard about that. That's actually the pretty bad, worst one we've had. That accident happened because they had a person that was involved in politics wanted to run a test at their power station. Now, this type of reactor is different than we have in this country. It was a graphite reactor, did not have a containment building, and the graphite reactor basically has a lot of water lines that run through the middle of it to produce heat, to produce steam, just like all the other power plants do. But what they were doing is they were doing a test to see what the capacity was on the turbine if they had to start it up real fast and shut it down real fast. And basically what happened, they got outside of the procedural guidance they had, they powered up the reactor too fast, and they had a steam explosion. So that steam explosion blew up the reactor, the graphite reactor, and because it did not have a containment building like we have in all the plants in the United States, it blew the building apart. And so what that happened is it vaporized part of the core. If y'all saw any of the footage from that incident, you saw people up on top of the building throwing things, debris back down into the building. A lot of that was part of the reactor itself. So they had a lot of deaths related to that accident, more than they really would ever acknowledge. But they had people picking up pieces of the reactor with their hands, throwing it down the building. So those people got exposed to a lot of radiation. Because it vaporized the core, we've heard of fallout before. It left a long trail of fallout through Europe where it contaminated the ground, it contaminated the animals, the water supplies, a lot of things. So basically, the results of that accident, had a lot of consequences. There's 2 towns that are still abandoned right now near that plant because of the radiation levels in that area. So there's 2 handouts that were back there. One of them talks about 3-Mile Island, this one, TMI. One of them talks about Chernobyl. So there's some information there that gives you details of what happened, so you understand that a little bit better. Now, at 3-Mile Island, a lot of people were very concerned about releases from the plant. And there have been studies done for the last 20 plus years looking at, did the population receive any radiation exposure that increased their chance of having cancer? And the answer to that is no. The actual amount of radiation that was released was so small they couldn't even detect it away from the plant. And they've done study after study after study in this area to make sure that the cancer rates have not changed from normal, to the population. All right. So then we'll get here now to the accident that happened at Fukushima. The nuclear plants at the Fukushima plant, they're all boiling water reactors. Our industry has a lot of boiling water reactors, and we have pressurized water reactors. The boiling water reactors are a little different because the water that goes through the reactor itself is actually the same water that turns into steam, goes through the turbine to generate electricity. All right, so if you look at, I don't know how many of these were, there's a little thing that says Farley up there. If you turn to the page 2, it's got a little diagram in there of what a power plant, the water systems look like, kind of. And PWRs, they have 3 different layers of water in them. They've got the reactor coolant system, which is the water that goes through the reactor vessel itself. That's what removes the heat from the fuel. Then it goes through a gigantic heat exchanger. It goes through and it heats up a second system of water, which is we call the feed water system. That's the water that turns into steam that actually rolls the turbines to make the electricity. So we've got 3 turbines that are tied in parallel together, and then as the steam goes through them, it rolls that up, and that turns the generator so we make electricity. All of the nuclear power plants work that way. They generate steam to make electricity. Just like the fossil plants, coal-fired plants, oil-fired plants, gas-fired plants. They all work the same way. All right, boiling water reactors, if you look at that diagram, they don't have that in-between liquid system. The water that goes through the reactor core actually goes through the turbine itself and goes back to the reactor core. Okay, so that's a little bit different. Because of that, they do have higher dose rates for people that work there because they're working on systems that do get contaminated from that contaminated steam. It's got radioactive water in it. So Fukushima, they had boiling water reactors. All right, and we'll go through and I'll show you what the plant looks like in a little bit. All right, so what happened? Back in March, they had a magnitude 9 earthquake off the coast of Japan. Y'all know that Japan has a lot of earthquakes, has a lot of tsunamis. They're in a high earthquake zone. Actually, this part of the country is about registered as a 0 for earthquakes. There's very small amounts of earth movement in this area, and the document that we have for Plant Farley has this area of the country rated as 0, which means basically they don't see any seismic activity at all. Japan has a lot of seismic activity. So when they built the plant, they knew that they had to build it strong enough to withstand a normal earthquake. And so they designed it like they do any other plants around the country and around the world. They take what they expect to be the maximum earthquake and they double that number. That's how they design the plant. All right, they did the same thing for tsunamis. They had a tsunami wall built around that plant. The biggest tsunami in that area they'd ever seen was 6 meters, so they built a 9-meter tall wall to protect the plant. But the tsunami that came through was 15 meters, so it went right over the wall. That was not what they expected to see. I don't have a copy of it, but I saw a video that was taken from one of the news agencies that was a little bit off plant site when the event happened. The wave, when it hit the buildings, went up above the tops of the buildings. The containment building is probably 150 feet tall. The wave went up about half again as high as that building, so it splashed pretty high. All right, so as you can see here, the tsunami struck almost an hour after the earthquake. Now the earthquake caused a lot of problems. It was a bigger earthquake than expected. It basically broke the power lines coming into the plant site. So they lost what the off-site power. We call that in the industry loss of off-site power. Basically, that means that you've got to power up your equipment yourself. So all these plants have emergency diesel generators. These diesels will start based on loss of voltage on the power in the plant, and they're there to generate electricity so that all the emergency equipment and all the vital equipment for the plant will continue to operate. Those diesels start within like 8 to 10 seconds, so they come up pretty quick. But in this case, they were fine. The diesel started up, all of them are operating. They have battery backup systems. They have battery chargers that maintain those batteries running. But when the tsunami hit, it flooded all of the electrical rooms at the plant. So all their diesel generators were below ground level. All their batteries were below ground level. When the tsunami hit and went over that wall, it flooded all those rooms. So basically, the plant was now on battery power. The batteries are designed to last about 2 hours for the plant. That's standard design worldwide. And they said they actually lasted about 3.5 hours, which is good. That means they did better than design. But after that 3.5 hours, they had no power. So they lost indication, they lost lights, they lost everything. And then they had no way to control anything in the plant anymore. With all the power lines down, they had no way to start any equipment. With the diesels flooded, they had no way to do anything. And so now they had to rely on natural processes to maintain the safety of the plant. All right, so here's a picture of the plant. You can see the 4 units here along the front, and 3 of those got damaged pretty bad. And then if you look along the edge of the water, you see these tanks. Let's see if I can see all these tanks here. A lot of that was their diesel fuel tanks, where they bring ships in to offload the diesel to fill the tanks. But they were down there in that area that got damaged too. And so after the tsunami went through, all those tanks were gone. So even if they had had the diesels not flooded, they lost their fuel supply. So they were still going to have a problem. All right, so this is one of the pictures of that area after the tsunami went through. Y'all saw the news footage. You saw that water just came in, with like a really fast flood. It was, 10, 15 feet deep. It, took out several buildings. It actually took out just about all the buildings that weren't made of some kind of stone or brick, and just completely devastated the area. That made it really hard for anybody to get in there to help the plant deal with its issues. All right, so some of the summary of what happened at the plant. Since they didn't have any power, they lost all their cooling capacity. Once the batteries died, they didn't have any backups or anything. Now, most of the pumps do not run off batteries. The indication runs off batteries, and valve control, like air-operated valves, will run off of batteries. Everything else is off of AC power. So with that, they didn't have cooling water going through the reactor anymore, so the fuel started heating up. Now, just like the plants over here, they do have a containment building. It looks a little bit different than the ones you see at PWR plants. But basically, it kept all that steam and the fuel inside of itself for a long period of time. But what happens as the fuel overheats, it starts creating a lot of hydrogen gas. Okay, so the fuel gets so hot, it breaks the water down into hydrogen and oxygen. And so they'll have basically a reaction occur, and once that hydrogen get up hot enough or a high enough pressure, normally they would vent that hydrogen off through a relief valve out of the containment building. But since they didn't have power, they couldn't do that. So what happened is the pressure got so high it actually damaged the valve, and they leaked hydrogen into the building around their containment structure. And that is what actually caused the explosions. And we'll look at some of those pictures in a minute. All right, so ultimately, once they got the fire department out there and some other help, they ended up pumping seawater through their building to help cool the reactors down, but they still didn't have a way to get the seawater into the reactor itself because it's still inside this containment structure. All right, so here's a breakaway view of what the reactor looks like at this BWR plant. And we'll go through some of the different parts. All right, so this red part in the center right there, that is where the reactor vessel is, where the fuel is. So that's where the water goes through that to generate the steam. Right around it, you see a little dome shape here, and it's just underneath this yellow concrete area. You can barely see the wall. That is what they call the containment structure, and it goes down and includes this torus area down here. That is designed to hold the pressure of all the steam if they have an accident, so they don't release anything out into the environment. Now what happened is that they've got, and that's what this primary containment is. Now this building here in green is an outer structure. All the way up to this floor is concrete, and this part here you can see on the structure is just steel. So it's like a tin building of some type. That's just to protect the crane and the fuel storage that they've got. Now the BWR plants, they have to unload the fuel from the top of the reactor vessel and then move it over into these storage pools over here. Those storage pools are concrete, they're lined with steel or stainless steel, and they're there to maintain the fuel underwater to remove the heat from it. But like at all the other plants, it's designed to have water force circulate through it. So in this case, they lost that ability. All right, so the whole world's concerned about nuclear power after this incident happened. They've been that way every time we've had an accident of some kind in the industry. So our regulator, Nuclear Regulatory Commission, they had all the plants in the United States go back through their design and look to make sure they met the criteria for seismic events, for flooding events, and had us go back and redo testing in some cases to make sure that the information we had in our design basis was correct. All right. So the President reported that all the plants in our country were designed to deal with, a lot of different things. Were designed for tornadoes, hurricanes, airplane strikes, everything you can think of that could be a potential issue at the plants. They've had to take that into account in the design of the plant. All right, so basically what every plant had to do within 1 month after this incident is go back and verify all that information. There are still documents coming out of INPO and out of the NRC to have us go back and test things and check things to make sure that we're where we're supposed to be safety-wise. Now, one of the differences is that Japan's regulatory structure is not the same as ours. I've got a chart in here that'll talk about that. They do not have the level of regulation that we have in our industry, in this country. All right, so some of the things that we looked at. We looked at earthquakes, we looked at floods, and other natural events, like I said, are tornadoes and hurricanes. High-level winds, you have to look at the wind loading on the transmission lines coming in and out of the plant to make sure we don't have any issues with something damaging the power lines. For a total loss of power, they're mainly looking at the loss of off-site power to the plant. Are your diesels going to operate like they're supposed to? Do you have enough fuel to run them for weeks at a time? And then in this case, for their event, can you get rid of that hydrogen gas that's generated if you overheat the fuel? Well, at the Fukushima plant, they couldn't because they didn't have any power of any kind. And then because of that incident, the other BWR plants are looking at the design of that vent that they've got on their containments to make sure it's going to operate like it needs to. All right, so some things that are a little different between us and the Japanese area. And in our country, NRC has required us to set up what they call emergency planning zones, and we have emergency plans that we have to deal with all the area around us. We have to deal with county governments, state governments, federal regulators, federal agencies of different kinds. And what we have to do is we've got it set up to where we've got, for our plant, we've got a 1 mile emergency zone, we've got a 5 mile zone, we've got a 10 mile zone, and then they've got a 50 mile zone. And what they do is they look at wind direction, what's going on with the temperature inversions. Is the air rising or is it coming back down the ground? And we're looking at the population. We have to know the population within inside that 10 mile zone. And we have at least four times a year we practice emergencies. So we bring our emergency plan staff in. We pretend that we're going through an accident of some kind. We have to deal with all the different agencies. We have to try to make sure we deal with whatever that's going on at the plant. And then we have to get to the point to where we're simulating evacuating part of the area because we may have a plume going out of the plant that's radioactive that could affect the population or affect the area. So that's some things that we do in the industry in this country. Besides that, the local, state, and federal government has a lot of different things that they have us do as part of those emergency plans. They've also got a security plan. They have to practice security events, and that came about after 9/11 happened. We added a lot of different things to practice to make sure that we can handle any kind of events that happen at the plant. All right, so radiation monitoring at plants. We've got, at each plant, we've got like 60 different radiation monitors looking at processes, looking at areas in the plant, looking at external things. And then we send out teams in pickup trucks to go verify out in the field what we're predicting is happening based on some software that we have if we had a release at the plant. We talk to the public about protection actions and evacuation actions, and the plant recommends to the local governments what we think the safest thing to do is, but then the local government makes the final decision whether they want to shelter people, whether they want to evacuate people. They may decide they want to evacuate more than we're recommending or less than we're recommending, but it's basically the government's job to decide what they want to do in the case of the emergency. But we've been trained, and we train them also, of the things that we look at and what we want to do about that. All right, so just an idea of what's inside of emergency planning zone, because they're looking at not just the people, they're looking at what it's going to do to the environment, what it's going to do to the industry around. So, you know, in our area, you know, we've got a lot of farming communities around Dothan. The plant near Vidalia, it's got a lot of farming community around it too. So we have to look at what is going to be affected if we did have a release from the plant. Now, one thing to note is we practice all this, we have to practice it all the time, but there has not been a release from any of the plants. The only one that had a small release was 3 Mile Island. The rest of the plants have not had a release. Now, if you go look at Fukushima and Chernobyl, they had some serious issues that did have releases of radiation. But nothing in this country has really had a release of any kind. We just have to make sure we can deal with it. All right. So, after the event in Japan, NRC got together with the Department of Energy, Department of Defense. They talked to INPO a lot. There's another group that's worldwide that's kind of like a sister agency, like INPO. It's called WANO, World Association of Nuclear Operators. And they look at all the other nuclear plants around the rest of the world. And they've all gotten together and they tried to find what experts needed to go to this Japanese plant to help them recover from this event. Now, one of the biggest things they had is because of the culture. You know, the Japanese government did not want to talk about what was going on there. And it's almost like they were afraid to talk about things. So we were trying to provide a lot of help, and they, you know, didn't want it for a while. But I think after the first several weeks, after they realized how serious the event was and that they were not going to be able to handle it themselves, they started letting people come help them. So based on this, NRC put together a document, because the Congress asked for it, about the safety of nuclear power in our country and what we needed to do to make sure we maintain that safety in our industry. You can pull that document up off the NRC website. It's usnrc.gov. It's about 500 or 600 pages. It's a pretty thick report. But out of that, they recommended a lot of different things to be done for us to verify that we're going to be safe to continuously operate the plants. And so we've had several different documents coming out telling us, okay, y'all need to go look at this area, you need to go run these tests, look at this equipment, may want to consider redesigning this. And so every month we've got documents coming out from the NRC and from INPO about things that the plants have to go do to make sure that we're going to operate safely, to continue to operate safely. All right, so some things that have continued after this event is that the NRC is they're constantly looking at the plants. If the plant asks for a power uprate where they want to produce a little bit more electricity, they're reviewing the technical basis for that and the safety analysis of that before they approve the plants doing that. They look at license renewal on plants. Basically, all the plants were designed to operate for 40 years, and then they were expected to shut down. We have samples of the metal of the reactor vessel that we've been taking over the years and analyzing, and based on that, we found that the metal of the reactor vessels has not deteriorated like they initially expected it to, and it's maintained its structure a lot better than they expected. So every plant now in the country has got a 20-year extension on the life of the plant, so they can operate for 60 years. Okay, so some of this continued after Fukushima. NRC continued their processes. They allowed these 2 plants, Limerick and Point Beach, to do a power up rate. Usually that's about 2% increase in power output. They granted licenses for Vermont Yankee and Palo Verde, so they can operate for 60 years now. And then the Southern Company is working on Plant Vogtle, 2 new units over near Augusta. And VC Summer over in South Carolina is looking at building 2 new plants also. And the licensing on those plants continued. And actually, last week, Vogtle was granted their combined operating license. That means they can actually finish building the plant and start it up and run it. So it's projected to be up and generating electricity by 2016. So they've just got 4 more years to finish building the plant and get it started up. So this is a good opportunity for y'all because they're going to be hiring 700 or 800 people in the next 2 years to run that plant. They'll look at people from a variety of different backgrounds. They'll look at chemistry people, health physics people, engineering people. They'll look at maintenance craft, so they'll look at I&C people, electricians, mechanics. They'll have security force that they've got to hire. A lot of different things are going to go on there. So that's a good opportunity for the area now. All right, and then NRC's also certified the design that GE and Hitachi put out for what they called the new advanced BWR plant. It's a little bit different design, puts out more power, it's a little bit safer. Now the plants that we're looking at building at Vogtle and at VC Summer are a new design. They're called AP1000s. What Westinghouse did is they looked at what kind of things could fail to cause us to have problems to safely maintain the fuel in the plant under an accident. And what they have done is they have designed the plant to where it uses natural physical processes to make the core safe. Instead of us having to start pumps and open valves and maintain tanks and all that kind of stuff, it's got a tank in the top of containment and a suppression pool in the bottom containment, and it'll have natural circulation going on with the hot water coming down and steaming back off again. It's going to remove the heat from the building using natural physical processes without us having to start pumps and operate valves. So it's going to make the plant a lot safer to operate just because it's a little bit different design. That design got certified last year by the NRC, and Westinghouse has been working on that for like 6 to 8 years. There's a lot of different things they had to do. They had to run a lot of tests to prove to the NRC that those plants are safe because some of it's new technology. All right, so you've got this big sheet that talks about power generation throughout the country. Okay, it talks about all the different types of power generation out there. It's got different types of fossil fuels. It's got nuclear power, biomass, hydropower, wind, and solar. Those are the most of the power sources that we use in this country. You can go around the world and there's people that use geothermal energy. Like New Zealand has a lot of geothermal energy because they've got a lot of volcanic activity under the island that they can use and get the heat that they want to generate the power. So if you look, a lot of people are wanting to move towards safer technologies for power generation. You hear a lot about solar, a lot about wind. Unfortunately, those are good technologies, but you've got to have a sustained wind for the wind turbines to work. For us in this area, you think we get a lot of sunshine, but if you look, we get a lot of humidity in the air also, and that kind of blocks some of the light. So that makes solar not as efficient here. That's why it works really well out west in the deserts. But of course, at nighttime, solar's not going to work. So right now, the most reliable sources of power generation worldwide are fossil generation and nuclear generation because they operate continuously around the clock, don't rely on the weather conditions. Hydro relies on enough rain being in the river to have enough water level to run those turbines. And of course, with wind, you got to have enough wind. There's a few places around the country that has enough wind for the wind turbines to be effective. And then solar, you got to have a lot of steady, pretty strong sunshine for them to work. So worldwide, most of the plants are still fossil fuel and nuclear fuel. Now in our country, nuclear is about close to 20% generation. Majority is going to be fossil of different kinds. If you go over to France, France is about 85% nuclear generation or higher. And China right now is leading the world in building nuclear power plants. They've got about 10 different nuclear plant units that are going up right now. And they are building nuclear faster than anybody else in the world can think about building. They're wanting to really change their economy and bring themselves up to the standard with the rest of the world. And so they know that nuclear power can do that really fast, really bring it up pretty well. All right, so some things to think about. You know, a lot of people don't want us building more power plants right now. The problem is that all the power plants we've got are getting aged. They're going to last so long, and if we don't start building plants very soon, we're actually going to start losing electrical generation in this country. If y'all have seen the news over the last few years about rolling blackouts and brownouts they had in California, that would be nationwide if we don't look at building new plants. And unfortunately, it takes 5 or 6 years to build a nuclear power plant because of all the licensing we have to go through. It takes 2 or 3 years to build a fossil plant. So, most of the utility companies in the country are having to look really far ahead to figure out what do we think our generation needs are going to be, when are we going to be retiring plants, and so they can look at when we need to be building new plants. And so that's why Southern Company chose about 4 years ago to start pursuing building the nuclear plants over at Vogtle. They had to look at fossil generation, they had to look at nuclear generation, they looked at hydro capacity, they looked at merchant plants. Basically somebody else would come and build a plant and sell us electricity. And what they found was that the nuclear plant, even though as expensive as it is, it's still cheaper in the long run for the Southeast and for the state of Georgia to have another nuclear plant built. All right, so let's talk about spent fuel. Spent fuel is fuel that's been through the reactor, usually 3 refueling cycles, so it's about 4.5, 5 years. And then we move it over to this pool to just remove the heat from it. The fuel is made out of ceramic material that's got uranium in it, and what we do is we enrich that uranium to between 4 and 5% U-235, so we can produce the fission that we want in the fuel. And the difference, a lot of people are concerned that the fuel in a nuclear plant is going to explode. All right, nuclear warheads, their enrichment is like 90, 95, 98%. So when you hear about countries that are using centrifuges to bring up the enrichment of their fuel, if they push it up into the 90s, they're not making fuel for reactors, they're making weapons material. Okay, so that's one way to tell the difference is that. Most of the plants in the country started out with an annual refueling cycle. So once a year they'd shut down, change out some of the fuel in the reactor, start back up again. When we were doing that on a 12-month basis, enrichment was running about 2.5%. So now we're running 4, 4.5, 5%. A lot of plants are running 18-month cycles. Some are running 24-month cycles. So they can generate electricity longer and just shut down once every 2 years or once every 18 months instead of every 12 years. So that makes us more economical to generate the electricity. So what do we do with the fuel when we get through using it? We move it to a spent fuel pool. So every plant in the country has a way to remove the fuel from the reactor, and they stick it in a pool like this. We've got pumps that circulate water through there. At the PWRs and most of the BWRs, they put boric acid in the water to help absorb the neutrons so that the fission process cannot continue anymore. And so that requires electricity for those pumps to operate. So at Fukushima, because they lost their electricity, they actually had the water start to boil in these pools because there's a lot of heat in that fuel for a long time. There's still really small amounts of fission going on those fuel pellets. It takes them decades for that heat to finally go away to where it won't do that anymore. So at Fukushima, they lost the ability to cool their fuel, so it started boiling the water, released heat, and as once that water level got down low enough, it started damaging the fuel. So they had a little bit of release going on because the fuel had actually gotten to where it was damaging itself. Now that's where most of the seawater was going that they were pumping, was going into the pool because the top of the building was damaged. They could spray water up in there and get the water down into the fuel and start removing heat from it again and cool it off. They did get into some of those pools and looked at the condition of the fuel, and actually the fuel was in a lot better condition than they thought it was going to be. They thought they had a lot of damage going on because of what was happening, and they actually found that most of the fuel was still in very good condition, still intact. All right, so there's two other things that we do to dispose of the fuel when we get through using it. A lot of the plants are now going to dry cask storage, and I think the Farley brochure had a picture back in the back of what dry storage canisters look like. They're big, tall concrete canisters, about 18 feet tall. We put spent fuel in those. We put 32 assemblies in there. It's got a double steel liner. They put helium in there and weld it closed, and they put it in this big concrete liner that sits outside. It's not an issue because the concrete and the steel block any of the radiation coming from the fuel, and the helium recirculates itself in there and removes the heat from the fuel. But most of the fuel, all the fuel that's in there is really old fuel that's already been in that pool for 15, 20 years. So it's had a lot of the heat already removed from it. All right, and then the other thing is that you've heard about Yucca Mountain. That was originally intended to go take the spent fuel from all the reactors around the country and put it in a cave down under the desert to where there's not any water table out there or anything, and just store it there until we wanted to decide what we want to do with it. Now, we've got options there. Because the fuel, even though we quit using it after 4.5, 5, 6 years, 90% of the material is still in the fuel. So we hadn't even barely used any of it. That's why France reprocesses their fuel. They'll go take the fuel after they've used it, they'll break it down, separate it back out chemically, and remake new fuel rods and put it back in the reactor again. And you can do that a lot of times before you start really reducing the amount of uranium-235 that's in your fuel. The only reason the fuel does not work longer than that in most of the power plants is because it's got neutron poisons that start developing isotopes in there. And as the uranium changes to different isotopes, it starts absorbing more of the neutrons in the fuel, and so it's not as effective to create the fission process that we want to have. All right, so let's talk about little differences between what Japan did and what the United States has done. All right, so after our 9/11 incident happened, we looked at fires and explosions and what they could do to the power plants. Okay, so there's a lot of stuff that came out of the government to the industry of things that we had to do. We had to change the way we handle security at the plants. We had to put up barricades at the plants. Actually, there's security fences at all the plants, and they had to extend those areas. And then they've got big concrete vehicle barriers out around the entire perimeter now at all the plants, just to keep vehicles from coming in and causing problems, so that they can't bring in drive bombs in and cause problems. If there was a terrorist attack for some reason, it would be a lot harder for them to get on the plant site and cause any damage. If you look at Japan, they didn't do anything. A lot of the world did not take actions like we took. All right, so you look at the NRC, they're a very large agency, 4,000 employees. They've got at least 2 people stationed at every nuclear plant in this country. They've got 4 regional offices, and then they've got the main office up in Maryland next to Washington, D.C. So they've got, they basically enforce the regulations on the industry that the government has. And they've got 2 branches. They've got a regulatory oversight branch, and then they've got an enforcement branch. The enforcement branch are law patrol, they're law officers. They come in with weapons, and they will arrest people, do whatever they need to do to make sure the plants are safe. And they can actually bring those weapons onto the nuclear plant site and if they need to, because they're allowed to. They're the only people that can, besides the security force at the site. All right, so in Japan, they don't have something similar to the NRC. They've got their regulator is part of their Ministry of Trade and Economy. So they don't have the same thought process and same regulatory oversight that we've got in this country. So our regulators are really breathing down our neck all the time, making sure we're following all the rules, following all the laws, operating things safely, and that's their job. That's what we expect them to do, because they're making sure our industry is the safest in the world. They don't have the same thing going on in Japan. All right, they don't have the same industry organization like we built. Now they use WANO. WANO does go to their plants and look at things, but it's not the same as what we created here when we made INPO back after 3 Mile Island in 1979. And then after 3 Mile Island, like I said, we built simulators at all the plants so that the operating crews could actually practice on something that was just like their control room, all these different accidents that we talked about. If you see a lot of different countries, they don't have those. They've got a generic simulator they practice that may not be like their control room. And so what they're practicing may not really help them a lot in how they respond to things. All right, so our industry here has taken a lot of short-term and long-term actions. Short-term actions are when we looked at our design basis and made sure that everything is where it's expected to be. We've got a lot of temporary equipment we use in certain accident scenarios. We had to make sure we tested all that, we maintained that equipment, make sure it would do what we said it would do. And then, Japan wasn't doing those kind of things. Long term, we're still analyzing what's going on from that accident. That's going to probably take years of research as we go through. We're going to look at the fuel, we're going to look at the condition of equipment in the plant, what happened to it, why did it fail, why did it work, whatever, and we'll use that learning throughout the world and improve the technology we're using at our nuclear power plants. I had one of the managers at INPO tell me one time something that was very true, as he said that the industry is no better than the least or the lowest performer, because if you think about it, the lowest performing plant is going to be one that gets all the attention. They're the ones that have problems, and the world is going to look at that plant and associate it with everything else. So it applies to any other industry the same way. So the nuclear power industry takes that very serious, and you'll actually have, if a plant is not performing where they want it to be, the chief executive officers of all the other utilities will come talk to the executives of that company and make sure they straighten themselves out, or they will ask them to shut the plant down. INPO has actually shut a plant down before. NRC has shut down plants before, and all of them have that ability, and they will do that to make sure that they get their culture back to where it needs to be to operate that plant safely, because we do not want people operating the plants in an unsafe manner. All right, so we're still continuing actions about how we can respond to different accidents. There really hasn't been anything different accident-wise that hasn't been looked at already. So we still already have events to deal with seismic activity, with flooding. In most areas, the flooding that we experience over here would be flooding from rivers. Out in Omaha, Nebraska, there's a plant there called Fort Calhoun. The Missouri River flooded last spring, and actually that plant was an island. The river came up around that plant and completely encircled it. So they had to build berms around that plant to protect it from the river. And they had one of those berms collapsed, and so it flooded part of the plant. So that plant shut down. It's been shut down now for almost a year, and they're going through assessing all the equipment that got flooded, and they have to fix all that before they start it back up again. So that's how serious the industry takes things, is they're making sure everything works like it's supposed to operate the plant safely. All right, so some specifics about Farley. It's 75 miles from the Gulf Coast. So even though we look at hurricanes, most of the time, by the time the winds get to our plant site, it's not going to be hurricane force winds anymore, but it can be tornadoes, and it can be high enough winds that we could have power line problems. We're about 155 feet above sea level. So basically there's only about 3 or 4 plants that a tsunami could potentially be an issue. And most of them are on the California coast, but even those plants are probably 150, 200 feet up on a bluff from the ocean itself, and so a tsunami is really not going to be an issue. For Farley, there's basically, it says low seismic zone. It's a no seismic zone. Basically, there's not any seismic activity at the plant in that area. We have had floods of the river at our site, but the plant is up high enough away from the river that it hadn't caused any problems of any kind. So it flooded some stuff down near the river itself, not any problems. It talks about here that Farley was designed to withstand a 0.10 ground force horizontal peak earthquake. That's pretty strong, and we don't really expect to ever see anything like that, but that's the minimum that we designed the plant to make sure we didn't have any problems. Okay, and it says here, that equates to a 5.5 magnitude earthquake, so we really haven't felt anything ever. They look back at over 150 years of recorded information about seismic activity and took whatever the largest was and then started magnifying that just to see what we needed to do. All right, and it says here on the entire Gulf, East Gulf coastal plain, nothing greater than 4.1 has ever been measured. So, don't have anything we have to worry about really. All right, so that's all the presentation I had.